is HL the same as KF? Is that right? FK? So effectively it's a composite function with three functions, three parts. Is it associative? Now you're probably suspicious that it is, and you're right, but how to prove that? So let's try to prove that. All right. I'll try another pen. Okay. So we'll try to prove these two, the left-hand side is equal to the right-hand side. So how to go about that? Now we can rewrite this by the definition of a composite function. We discussed a bit earlier. So we can rewrite this in the following way. So this is H, binary operator G, it gets applied to f of x. Okay? And we can rewrite that as H applied to G of f of x. By composite operator definition. Alright, now let's take, so that's the left hand side. Now let's take the right hand side. That's this. So we have H of G of f. We can rewrite that as H of G f of x. And that's the same as your left-hand side. Or I can put a bracket around there. And similarly here. Okay, but these two are the same. All right. So we've shown associativity. So if you have three functions, they're associative. So you don't have to worry about where you put the brackets. You just forget about the brackets. Okay. So next question. So we've proved the associativity, and now two more theorems on the idea of if you try to take the inverse of a composite function. So you got something like this. Not showing. I may have to get a completely new pen. I'm using older ones, hoping that, right? No, that's not bad. All right. A, B, and C here. Okay. And you're mapping F, and then you're mapping G. So your composite function, so if you go direct, call that H. Right? So your composite function, H, is GF. Right? GF. Again, remember the order. Right? The right-hand one is the one you use first. So you do F first, and then map to G. So F first, then G. So H is GF. Right? Question: what is H inverse? What is this? Question mark. What function takes you back directly from C to A? What is this? Now, f and g are proper functions, okay? Oh, wait a minute, I think I need to assume f and g are bijective. Just a minute, I need to check that. Yes, yeah. Now suppose that the functions f and g are both bijections, right? That's in the text. All right, now from theorem 30 and 31, if f from here to here and then g from here to here, if those are both bijections, that means that both f and g have inverses, unique inverses, right? So in other words, there's an inverse f that will take you from B back to A. And there'll be an inverse G that will take you from C back to B. So you've got something like this. That will be G inverse. Okay? And from B back to A, that will be F inverse. I hope you can hope you can follow this. Here, look, now look, this is getting messy with Venn diagrams and circles or ovals. There's a more compact way of. We don't need circles anymore. We can just use dots. See, we're talking about functions now. We're not so interested anymore in the elements of a set. So we don't need Venn, V-E-N, diagrams anymore. We can represent a set now as just by a dot, and it's sort of cleaner. Yeah, watch. So that's set A. Okay. So this dot. So dots now represent sets. Okay. So that dot there represents set B, and this dot's C. All right. So that was F. Okay. And that was G. And H, the composite function, that's H. Now what is H? Well, it's GF, okay? And remember, the right-hand side goes first. So do F first, then G. So in a composite function, you look at the right-hand side. That's your first operation, first mapping. So you do F, then do G. All right? So H inverse equals what? Well, what do you think it's going to be? What's your hunch? I mean, you imagine you're a mathematical researcher, right? And you're dreaming this up for the first time. What's your hunch? And then try to prove it. You have this hunch. Well, I think it's probably going to be such and such, and then okay, that becomes your theorem statement. This is true. And then you have to prove it. And if you can prove it, if you have your theorem statement and the proof, then the whole thing, the package, the statement plus the proof, that is a theorem, right? Proved. Okay, well, what's your hunch? So H, to go back here, H inverse. Now, you see how this is so much tidier than this mess? I mean, I did deliberately pretty messy anyway, but especially on this tiny board. I'll be very happy to see the last of this board. It's too small. I think it was a mistake, and also the quality is very low. So I'll spend a bit more money on the next one and make it sure it's much bigger and higher quality. Okay. So what's your hypothesis for H inverse going back? Now, look, we know this. We know going back from C to B is the inverse of G, so that's G inverse, and going from B to A, its inverse is F inverse. Okay, so FG, then so probably to go back, right, directly from C to A, this composite function, this inverse of A, if H is direct this way, then probably the inverse direct, well, going backwards, H inverse will probably be what, would you say? Well, you probably do G inverse first and then F inverse second, right? So that will be F inverse G inverse. Okay? Again, remember the order. What's on the right hand side gets applied first. So you apply G inverse first, takes you to B, and then followed by F inverse takes you to A. So that's your hypothesis. Right? That's your hypothesis. So theorem 33 will be to prove that this is your inverse for the composite function, for H. H is your composite function. H has parts, right? It's composed of something, composed of two things. It's composed of two functions, f and g. So your inverse composite function will be composed of g inverse and f inverse, probably. All right, so theorem 33. Well, I better, again, I need to clean the board. So we'll prove theorem 33 when we get back.